Alright, confession time. I always found myself to be very good at probability and stats. In fact, back in high school, I was often the butt of jokes whenever we studied stats. And I don't say this out of pity, but it points to a feeling that I've seen a lot. Probability is somehow this alien field of math that is so different from everything else. It requires a different skill set. It doesn't make any sense. But why? What can we do to make it a little easier to learn? I think most of the courses I've taken in college that cover probability theory do a good job at teaching things from the ground up every time, but in reality, this is a field of math that many people will run into. The Intro Data Science course in my alma mater will give you the most diverse set of majors you'll find anywhere on campus. It's clearly a skill that a lot of folks want or indeed need to learn. And since you need a solid understanding of probability to excel in data science, I think there's some work to be done in how we teach it. So then, why is probability so hard? Maybe it's that probability is just not very well defined. It's one of the first things that you were taught in any good probability course. There are competing schools of thought on what it really means. Let's say, for example, I wanted to estimate the chance of this video blowing up. If I were to say 10%, where does that number come from? Am I just going for 10% because it's a fairly small number that happens to be nice and round? This situation is quite complicated, as you can imagine, since there isn't really a lot of data you can collect for it. So let's try something else, a little bit more basic. Every probability student's favorite tool, a coin. Let's say there's a game that involves flipping a coin with 60% chance coming up heads. And it's just very simple. If you get a head, you win. If you get a tail, you lose. So let's say that you wanted to confirm that the win rate is indeed 60%. What would you want to do? Well, you'd probably want to play the game a large number of times, right? And hope that the proportion of those games that result in wins comes out to something near 60%. This idea of a long-run frequency was the first real understanding of probability that took hold, and it gave us things like the normal distribution, the central limit theorem, and indeed the law of large numbers. The weak one, at least. But something's missing here. Suppose you aren't told the win rate of the game, and you observe some data on a sequence of wins and losses. Now you want to work out what the real rate is. A good starting point is to just guess. And it's all fine and well making a guess, but how do you know if your guess was good? The common practice for this is to calculate how likely the data was given your guess. And just like that, you have the framework for Bayesian inference. Now, whether or not you believe probability is a long-run frequency or something you can just guess and update based on evidence doesn't really matter for doing calculations because there is a specific language of probability that everybody uses. You guys know what an axiom is, right? It's a fact that is solely true because we say it is. For math to work, we count on these axioms to govern what is possible. In theory, anything can be derived from them. It turns out that probability theory has axioms of its own, but before we talk about them, let's cover the difference between an outcome and an event. An outcome is just one possible result of your experiment, and every single outcome has its own probability. Outcomes must be mutually exclusive, which means that they don't overlap, and they must also cover every single possibility from the experiment. An event, meanwhile, is a subset of outcomes. This subset can have just one outcome, more than one, none at all, or maybe even every outcome. The point is that events can be whatever you want them to be, and the probability of an event is the sum of the probabilities of all of the outcomes within that event. So with that, here are the three axioms. The first one is that the probability of any event or outcome is at least 0. That one seems to be pretty trivial, but it's important to state. The second one is that the probability of all the possible outcomes is 1. In other words, if you made an event that covered every single outcome, its probability would be 1. And finally, if you have mutually exclusive events, which is to say events that don't overlap, the probability of their union, which means the probability of at least one event happening, is simply the sum of the individual events' probabilities. This is because there's no overlap when events are mutually exclusive. So you don't have to worry about events happening at the same time. And there you go, that's all you need. From these three axioms, you can prove a lot of things in probability theory. And when I first learned about them, I was surprised. I felt like something was missing, because these statements seem really basic. But it turns out that you can derive many things from the axioms. Let's start with the complement rule. Every single event has a complement associated with it, which is the event whose outcomes contain every possible outcome that is not in the original event. I'm denoting it using an apostrophe, but I have seen so many other ways of denoting it. Anyway, we claim that the probability of A complement is 1 minus the probability of A, which makes sense intuitively, but you can prove it using the axioms. Because A and A prime cover the entire range of outcomes, It's either the case that A happens or it doesn't. There is no third case. And also, you can't have A and not A happening at the same time. So we apply axioms 2 and 3, and we find that the probability of A or not A is the probability of A plus the probability of not A. We know that they cover the entire set, so they have to add up to 1. Then just rearrange the equation, and you have your original claim. Now let's look at the case of union and intersection. From here on out, I'll be using the U symbol to mean union, and the upside down U symbol to mean intersection. We know what happens when we have events that are mutually exclusive in terms of their union, but when they're not mutually exclusive and there's a chance that both can happen together, we need to account for that in our calculation when we're trying to find the union. So let's try and prove this claim about the union. If you look at a Venn diagram, it's pretty easy to see. If you just add the A and B circles together, you will notice that the intersection bit is counted twice. So to account for that, we just subtract the intersection once, and we have our answer. But how would we prove this using the axioms? One thing we might want to do is to try and rigorously define what the union looks like. We can divide this into 3 different regions. It's the intersection, plus the part of A that's not in B, plus the part of B that's not in A. There's a special operation in set theory called the set difference, which basically means all of the elements that are in one set, but not in another. And the set difference will help us here to specify which events are in A but not B, and B but not A. You notice that we have these 3 separate events, and they are all mutually exclusive because you're either in A alone, B alone, or both A and B. If you're in neither A nor B, it's not relevant to the union, so we ignore those. So we can add up these events using the third axiom. Now our final answer shouldn't have set differences in it, so let's try and rewrite the set differences. The probability of A and not B can be taken as the probability of A minus the probability of the intersection, because everything that's in A is either in B or not in B. So we subtract the ones that are in B to get the ones that aren't in B. And the same applies for the set difference of B and A. So now we can put everything together and we have this expression here. And after combining some like terms, we get our original statement. So that was quite a lot of theory, but I mainly talked about it all because on the outside, probability seems like this really abstract thing, and it sometimes does feel that way, even if you've studied a lot. But just going back to those basics sometimes, seeing how you can prove things you know using the most simple facts, can be quite rewarding. But now, we're getting to the good stuff. Let's talk about the Monty Hall problem, which you're probably tired of hearing about by now on probability YouTube videos. But just in case you haven't heard of it before, it's a game show where you're presented with 3 doors. Behind one of them is your dream car. Well, probably not for me because I'm a public transit simp. But anyway, behind one of the doors is your dream prize, and the other 2 have things you don't want, usually goats. So you choose one of the doors, and then one of the other doors you didn't choose is open to you. And crucially, the door that is open has a goat behind it. So now the host asks you, do you want to stick with your original choice, or do you want to switch to the third door that I haven't touched yet? And it turns out that in 2/3 of cases, switching is the right thing to do. Even though to an outsider, you might think, oh, there's 2 doors. You just pick one at random. It's a 50-50 shot. But it turns out that switching is better. The advice that I've commonly heard given to people who don't understand the logic of Monty Hall is to think of more doors. So instead of 3, you could go up to 10. Instead of the host opening 1 goat, you're now shown 8. Switching is still the right choice in this instant, but with a much better chance of success. However, in my experience, this advice which is given to add more doors is not always helpful to people. It helped me the first time I learned Monty Hall, that's for sure, but someone who isn't convinced about why you should switch into 3-door case could easily come to the conclusion that it's still a 50-50 choice between the 2 unopened doors. So in that case, adding more doors made things even more confusing. What would really help is to understand why exactly switching is better in the 3-door case at all. And there are many ways that this has been explained, so I'm not going to go too deep into it. You're probably tired of hearing about Monty Hall. But basically, you can treat this scenario as 3 numbers. 1 number being the door where the prize is, 1 number being the door that you chose, and another number being the door that the host opened after you chose. There are 3 cubed or 27 possible triplets, but not all of them actually work in this game. The first and the third ones can't be identical because the host will never show you the prize. And the second and third can't be identical because you'll get a different door open to you than the one you chose. So with the triplets that you have left, think about the probability of each one of these showing up. Now I'm going to use a little trick that we call symmetry, or in other words, without loss of generality, and we're just going to take the cases where door 1 is the door with the prize. We're allowed to do this because it doesn't affect the logic of the proof if we just set one of the doors to be the prize door and proceed from there. If you set door 2 or 3 to be the prize door and do the math, you will get the same numbers. And crucially, we're assuming that the prize is equally likely to be behind any of the 3 doors. Otherwise, we wouldn't be allowed to do this trick. So, now that we have 4 triplets, let's work out the probability of each of them showing up. Let's start with this one, the 1, 2, 3 triplet. Since the prize is fixed at door 1, that doesn't influence the probability. But if you pick the door at random, let's say there's a 1/3 chance you pick door 2, which makes sense. And now the only door that the host can open is number 3, because 1 is the prize, 2 is the one you chose. So that doesn't add anything else to the probability, so we get 1/3. Similarly, the 1, 3, 2 triplet works out to 1/3 because you pick door 3, the prize is in door 1, the only door that can be opened is 2. The more interesting case is when you pick the door with the prize behind it. Now the door the host opens isn't fixed, it can be either 2 or 3, and we assume that they happen with equal probability, so these 2 triplets have a 1/6 chance of occurring each. Finally, let's split these into cases where you should and shouldn't switch. It turns out that you should switch when the door you chose is not the prize door, so the bottom 2 cases, and you shouldn't switch when the door you chose is the prize door. If you add up the probabilities within each of these 2 boxes, you'll find that switching is the right thing to do 2/3 at a time. So let's look back and reflect. What did this exercise teach us? Well, a good first step when you're stuck on probability is to think about all the possible ways an experiment can happen. We often call this the sample space. In our case, that was recognizing that we can represent the game as 3 numbers, but also recognizing that most of those cases are redundant. Of course, sometimes you can reduce the sample space even further by using some kind of argument with symmetry. And then once we do that, we can create some events, such as switching or not switching, find out which cases belong to each event and find their probabilities, and then add up together all of the cases within our desired event to get the final answer. Let's see if we can apply what we learned now to another popular probability problem, the birthday problem. Now, one thing I should say is the method I'm going to be using in this video has a very slight mistake, and this is on purpose to illustrate an issue that you might run into when you work with probability. My challenge for you is to see if you can find the mistake before I tell you what it is. So, if you're not familiar, the birthday problem is when you have a group of n people in a room, and you ask all of them what their birthdays are. You want to find the probability that any 2 people share a birthday. And what makes this problem interesting is to find the smallest value of n, or the smallest number of people you need, such that the probability of 2 people sharing a birthday is larger than 50%. You might think this number would be fairly large, but it turns out to be pretty small. So, let's start. What is our sample space? What are the possible outcomes? You might think, let's make a list of every single person's birthday. But that's a bit redundant because we don't care about the dates themselves. We just care if 2 people happen to have the same birthday, regardless of date. So let's try something else. Let's say instead of working with individual people, we work with pairs of people. And then we ask each pair one at a time, do you guys share a birthday? If they do, mark a yes, otherwise mark a no. Now we need to find out how many pairs there are, so we can enumerate all the possible events. Well, for the first person in any pair, you can choose anybody, so you have n choices. The second person has to be anyone but the person that you didn't choose, so you have n-1 choices. But now you'll notice that we have double counted, because the first and second person and the second and first person are the same, so we should divide our answer by 2, because the order doesn't matter, and we get n times n-1 over 2. Now this number actually has a name. It's called n choose 2. And the more general form, n choose k, pops up quite a lot in probability, so it's a good thing to know. So, let's take a look at our possible outcomes in the sample space. They're going to be strings of yes and no, 1 for each pair. And we just worked out that there are n times n-1 over 2 pairs. So, which of these outcomes are relevant to the question? Well, we want at least 1 person sharing a birthday, so we want every string with at least 1 yes. But there are way too many strings that fit that description. So to make our lives a lot easier, we can use another trick in probability, which is to flip the problem around. The opposite of at least 1 pair being a yes is all pairs being no. So we can find the probability of the all no string and do 1 minus that to get our actual answer. So, what is the probability of 1 pair being a no? Make the first person's birthday whatever you want, it doesn't matter. The second person's birthday has to be one of the other days that the first person's wasn't. So the probability of a no is therefore 364 over 365. And now we have n choose 2 pairs, so all we need to do is raise 364 over 365 to the n times n minus 1 over 2 power, and there is our answer. Let's type it into Desmos and find the smallest value of n for this number to exceed 50%. And we find that n is 23. That might be surprising to you. 23 people is all you need for the chance to be better than a coin toss? And that's not all. Look how fast this number grows. You can see it gets very close to 1 before we even hit 100 people. And the reason for this is very simple. If you look back at our formula for the number of pairs, n times n minus 1 over 2, and expand it, you'll notice there's an n squared in there. The number of pairs is proportional to n squared. That means it grows at a quadratic rate. So that is the birthday problem, right? Well, as I mentioned earlier, there was a mistake in my calculation, and now I'll explain what that mistake is. And it turns out it's in this step where we actually multiply the probability of a pair being a no. It turns out we have made a very dangerous assumption here, which is that every single pair is independent. And that might be a nice thing to think, if every person's birthday is independent, then surely the pairs are independent as well, right? Well, think about this. If 1 and 2 share a birthday and 1 and 3 share a birthday, then what can you say about 2 and 3? So clearly, there is not full independence here. And this is a very common pitfall when you're solving probability, assuming independence. You can only multiply things out like this when they are independent. And this is why this approach to the birthday problem is not the one that is actually used. So now let's talk about the actual method to solve the birthday problem. We still want to look at pairs of people, but instead we're going to add each person one at a time. And crucially, we're going to stop the experiment as soon as we find one match, because that's all we need. And as we saw earlier, sometimes if we have multiple matches early on, that can kill off some of the other probability terms that might depend on those earlier matches. So let's start with the first two people. As we went over earlier, the probability that they share a birthday is 1 over 365, and that they don't share a birthday is 364 over 365. If 1 and 2 do share a birthday, we stop what we're doing and conclude that the experiment is a yes, there is a match. But if not, we go on to the third person. So what is the probability that person 3 shares a birthday with 1 or 2? Well, we're going to assume that 1 and 2 don't share a birthday, otherwise we would have stopped. So we have to add that extra 364 over 365, then multiplied by the probability that the third person takes any of the 2 days of person 1 and 2, because again, we're assuming they don't match, there are 2 possible days, so we get the 2 over 365. And then similarly, the probability that 3 doesn't share a birthday with 1 or 2 is just going to be 1 minus that, so we have 363 over 365. And in case that's not clear, let's add a fourth person. Once again, we're only going to get here if 1, 2, and 3 don't match. So now 4 could be any of 3 possible days if they're going to match, but we still have to multiply all of the probabilities that we had before because we are assuming that we got to this stage and ruled out the cases where 1, 2, and 3 have matches. And hopefully now you can start to see a pattern emerge. If we continue this all the way up to n, we will have in the numerator 364 times 363 times 362 all the way down to 365 minus n plus 1. And in the denominator, we're just going to have a bunch of 365s. So you have 365 raised to the power of n minus 1. Once again, this is the probability of no people sharing a birthday within the first n. So we have to do 1 minus that to get our final answer. But first of all, let's simplify it into a neat product notation. If you've never seen this notation before, it's a lot like sigma notation, except instead of adding things, you multiply things. We can plug this into Desmos, and we find, once again, that the answer is 23 people. The numbers that we get for this formula are extremely similar to the ones that we got earlier. They're only off by a few thousandths. And we still got the same threshold of 23. But of course, we won't always get this lucky. So let's recap what we have learned from these 2 attempts to solve the birthday problem. The first big red flag is that independence is a dangerous thing. You can't always assume it, and when you do, you should try and convince yourself that the events are indeed independent. And of course, on top of that, we saw a use of combinations, a really important tool in counting and combinatorics. This is one of those things that is quite helpful in probability that I think sometimes doesn't really get taught enough before people go into probability courses. And finally, we saw how if you're only looking for one instance of a success of an event, you can stop the experiment early, and this greatly reduces the sample space and also ensures that you won't have issues down the road with transitive events. So, after all of that, why is probability so hard? To me, at least, the way I'd answer that is that probability is very involved. When you're solving a problem, there are a lot of steps that you have to take and a lot of careful actions you have to consider when you're laying out the space and the events and you're trying to combine things together. You have to think about independence all the time. You have to think about a counting argument. You have to think about potential symmetry. And this can be a lot, especially if you're not really brushed up on the fundamentals. Probability and discrete math go very well together. In fact, my university decided to combine them into the same course during one whole semester. And in hindsight, that was not a good idea. It ended up teaching both of those subjects very poorly. But the bottom line is that they are very closely related, with things like graph theory, counting arguments, and set theory all super important. And also, probability isn't really something that you can just drill and practice a ton just by doing repetitive questions, because every single one is so different. It's not like you can just open a textbook and do 50 probability questions in a row, like you can, say, do 50 derivatives or 50 determinants or whatever in some other field of math. Every probability problem is its own ride with its own unique perspective on things. And that can be quite fun, but also maybe a bit stressful. And it's a very exciting field once you start to master things. I do plan to make a couple more videos on things that I find interesting in probability and stats later down the road. But for now, if you are learning probability yourself right now, then good luck. I do have some creators on YouTube who make great videos about probability and stats that I would recommend checking out. I have put links to their channels in the description. And of course, if you want to see more of my work for whatever reason, then stick around. Hopefully, I will actually get a consistent schedule going now. It turns out that saying the word probability a lot gets very hard. Yeah, look at that. Maybe this was the reason why I titled the video that all along. I mean, 3 bilabial plosives all in a row? That must be very annoying. Wait a second, I don't make linguistics videos. At least not yet.